Welcome to a lesson with Dr. Powell. Let's take a look at an example of finding a right inverse to a function. Suppose this is our matrix function right here, and under the column interpretation, it's a function that has domain R3 and codomain R2. It's a linear transformation, and it is surjective. Its Smith normal form looks like this. Its range has dimension 2, which is all of the codomain, so it's surjective. And we would like to actually find a right inverse for this matrix function. We know it has a right inverse because it is surjective. A right inverse is a function or a linear transformation that goes back the other way, such that when you compose it like this, so you first run this guy and this guy, that's the same thing as just doing the identity on R2. Now, in terms of matrices, this means that, so we run a function before f, that's like we multiply a matrix over here, call it like C. Okay, so we're going to multiply a matrix on the right, and the result when we do that, so it's like we run this function, then that function is going to be the identity function R2. So we're going to get ones down the diagonal, zeros on the off diagonal. Now, what is this good for? Finding a right inverse, which we're going to represent as a matrix. Now, it's good for finding an element in a fiber. Suppose you have something over here, some vector in R2. Maybe you have a system of equations, and these are your equations. And then you with x, y, z is so these are the coefficients, and it's equal to something on the other side of the equal sign. Well, what's on the other side of the equal sign is like what's over here. And finding just one solution, not all of them, but just one solution to the system would be like throwing that into your right inverse and landing in the domain, and that'll actually give you something that's in that particular fiber that actually is a solution. So not all the solutions, but it will give you just one solution. Then to find out the rest of the solutions, you just add by any vector in the kernel of this map F. So if we could find the kernel, we just add that to that specific solution, and we can get a specific solution simply by applying this right inverse. So how do we find this right inverse? Well, we're going to be running multiplying on the right, and we start by thinking of column operations. That happens before as isomorphisms before this matrix function, and we want to apply these column operations in order to get down to Smith normal form, which actually is obtainable because this represents a surjective function. Just by doing column operations on a surjective function, you actually can achieve Smith normal form. So in doing so, let's see what we can do. We can airdrop, let's see, this one going down to get this 0, and that is 0, especially since that's a 1, 0. Now, whatever we do here, we're going to do to the identity matrix on R3, okay? I'm going to do the identity matrix on R3. And the column operations that we get here are actually not going to be the right inverse, but it's going to help us figure it out. So we're going to apply the column operations to the identity matrix, and that's actually going to give our column operations matrix, which will be a map or function from R3 to R3. Then all we have to do is just modify this in a way so that we actually get a right inverse with the right domain. Okay, so proceeding, we can airdrop this way. Okay, so multiply by -1 and go that way. So if we do that, we do the same thing to this as that. Okay, so this will become a 0. Then we airdrop again here. So this 1 going to the, so by -2. So we'll do that over there as well. -2. And then this guy over here will be a 0. All right. Then we can airdrop right here, this 1 going that way with the -1. And so doing so over here, so 1, you'd get a -1. And then you multiply this by, I mean, you get a, sorry, what was that? Yeah, you get a -1, that was right. And then right here, multiply by -1, which would be +1 plus the -2 would be a -1 right there. Okay. Be a -1. Okay. Then, and doing that actually put us in Smith normal form. Okay. All right. So now notice that we have this. So we have a column of zeros right here. The corresponding column is right here. Now, if we were to remove this, remove this specific column right here, we'd actually achieve our results. So we look at the zeros and we just kind of cross out that column. I mean, why does this work? Well, even if you thought of this as terms of a row interpretation, we're just adding these rows together. And as we add these rows together and we want to be able to end up with this. Well, the third entries is what's extraneous, and that's not what we want. But over here, as we add, we should see as we add accordingly to what's the scalars that are over here, the row interpretation, we should land with this, which is exactly what we do. So the right inverse is actually 1, -1, 0, 1, 0, 0. And we have just computed a right inverse for this matrix. Thanks for watching.